And first of all, I wanted to thank the organizer for inviting me. And as Gary said, today I'm going to talk about something I think pretty much on topic for this workshop, which is work with Michel Mange from the University of Amsterdam. So this work started motivated by the backbone of the internet and routing and load balancing in this backbone. So for example, here we have the OVH Europe network, which is kind of a private network, part of the backbone of the internet. They operate data centers, and they're all fiber optics all across Europe and the world. And what I think it's important of this network and many others in the backbone of the internet is that the traffic that they handle is, of course, very highly aggregated. They serve hundreds of millions of people. And the other important fact is because the traffic is so highly aggregated, it's not possible to do any sort of flow level or packet level routing or load balancing. So the routing and the load balancing these networks are done in a mostly static way. Like they just need to decide what fraction of traffic goes where. And as applied probabilist and Q theorist myself, I would like to do very streamlined model and try to get insights out of this model. So a very stylized model of the problem that they have is of static load balancing. Right, so on one hand, we have the data center. So you have a bunch of servers, K servers in this case, with possibly different processing rates, and each one with their own queue. And on the other hand, we have that work of different types arrive to the network and need to be serviced by one of the servers. Right, and for each type of work, we have a router that needs to decide which fraction to serve to different servers. And in principle, there could be compatibility constraint of the type of work and the server that could service them. But for the purpose of this talk, we're going to assume that everyone is compatible with everyone, and that's not an issue. So because the traffic is highly aggregated, one of the assumptions that we make is that the arriving work, so the process A, is actually an m-dimensional Gaussian process with some known rate lambda, which is a positive vector in Rm, and an unknown covariance matrix that for Gaussian process is, instead of for Gaussian random variables, you have a matrix. Now here we have a function from R2 to the real matrices. And these two completely characterize this Gaussian process. So this is kind of a functional central limit theorem approximation of what the highly aggregated traffic would be. And the second assumption, kind of reflecting the features of these networks, is that the routing is going to be static and deterministic with some routing matrix R that essentially tells you what fraction of each type of work goes to each one of the servers that we have. And the objective here is to learn what's the optimal routing matrix in terms of a minimax problem. So trying to minimize the maximum probability of overflow of certain buffers. So here we're saying what's the probability under the routing matrix R that the queues go above a certain threshold. We want to minimize the maximum of that across all servers. And this could be kind of from a quality of service perspective, that we don't want to go above certain threshold because that will incur delays, and we want to minimize the maximum of those. A few further assumptions that we put on this array of process A is that, again, because the traffic is highly aggregated, we assume that we're in what's called many sources regime. And that means that the arriving process is actually a superposition of a very large number of IID arriving processes. So it's the X are all ID, and the red process is a superposition. You can think of N being a very, very large number. And again, for the purpose of this talk, to keep it simple, instead of considering any Gaussian process, we're going to consider a much smaller class, which are the fractional Brownian motions. And what's particular of them is that the covariance matrix has a very particular form. They're this polynomial, which is parameterized by h, which is called the Hertz parameter between 0 and 1. And here, if we take h equal to 1/2, we have the popular Brownian motion. So it's a particular case of these fractional Brownian motions. And then if h is bigger than 1/2, we have what's called long-range dependent processes, which are processes that are essentially positively correlated in time. So if we have a lot of arrivals in one interval of time, then it's more likely that we have more arrivals in the next. And h less than 1/2 are short-range dependent processes. That's the opposite. They have kind of a negative correlation in time. So if you have a lot of arrivals in some interval, you're more likely to have less arrivals in next. And h equal to 1/2, the Brownian is the case that they're independent. So there's no positive or negative correlation. And here, as with Gaussian random variables, we have some variance for the process and correlations in between the different coordinates of the process. So the processes themselves can be correlated. So the issue still stands. How do we find this optimal routing matrix when the arrivals, we assume them to be Gaussian? Well, one approach that we take is to directly learn the model parameters. So for example, we can observe the arrival process and directly estimate the covariance matrix, right? So if we do that, then okay, now we know all the characteristics of the process, and we can use large deviations approximations to get this probability of overflow, which is going to be pretty accurate because we're in this many sources regime that I talked about. So this is going to be a pretty good approximations, a large deviations. And then now we have this as a function of R of any routing matrix. We could just solve directly optimization problem for R. So we kind of solve it directly. And the advantage is that we essentially only need to estimate things once. Once we get the covariance matrix, we get the optimal routing matrix. But the disadvantage is that it's actually hard and sometimes impossible to directly estimate the covariance matrix. And that is because if you want to estimate the covariance for some time t, then you need to sample the arrival process every t units of time. And if t is very small, then you need to be sampling it quite quickly, which might be unfeasible in practice. And also for different times, you need to sample the process at different times, so it becomes very, very troublesome. So a different approach would be, okay, we don't need to learn the system parameters, we just need to learn what's the best routing matrix. So you can start with some routing matrix R0, then observe now the queues instead of the arrival process and estimate the overflow probabilities for that particular matrix, and then implement some sort of algorithm, your favorite algorithm, that will iterate over different routing matrices until it converges to an optimal one. The advantage of this is that the queue lengths are much easier to estimate than the covariant matrix when done directly. But the disadvantage, this is possibly slow to converge because you need to iterate with different routing matrices and do an estimation step for each one of them. So it could take a long time. So what we do is actually kind of trying to get the best of those worlds with some indirect learning. So what we do is, well, we start with some initial routing matrix R0, which we can pick to be stable because, or stabilize the system because we know the arrival rates. We observe the queues and estimate the steady state Q length distribution under that routing matrix R0. And then the key is that we use an inversion procedure to obtain the covariance matrix based on the steady state distribution of the Qs. And this is kind of the key part, the key ingredient of this method. And once you actually get the covariance matrix, then you can do the same with the first approach and use large deviations approximations to get the probability of overflow as a function of any routing matrix, and then solve the optimization problem directly. So with this, we get the best of both worlds. We get that we estimate Qs instead of the covariance matrix, which is easier to estimate. And then it has fast convergence, because once we do this inversion and obtain the covariance matrix, then we solve it in one shot. We just solve for R star, and that's it. The vast majority of this talk will be dedicated to talk about this key issue, this inversion procedure that we do. So we're going to talk about two procedures. The first one was kind of the idea of the inversion procedure, at least was in this paper from 2009 by Manges and Van de Ment. They had the idea to do this inversion, but they didn't really prove that it worked. So they provided mostly simulations to back up their procedure. But now we kind of adapted it and proved that it actually works as intended. So the idea is that the workflow in this type of system goes as follows. You get the arriving work, which is an m-dimensional process A. Then through routing, you get the input process to the ith Q, I sub I. And then through queuing, you obtain the kind of the steady state distribution of your Q length. And what we want to do is an inversion that essentially takes the steady state Q length, and in this case, the marginal distribution of the whole Q length, just for the ith Q. And in some way, we're trying to get the variance of the input process. That's kind of sort of the thing that we're trying to invert. And this is based on this large deviation principle. This is kind of well known for single server queues with Gaussian input. Is that the limit of 1/n of the log of the probability of going above any threshold in steady state. It's the infimum of this function, where B is the threshold that you're going over, mu is the service rate of your server, lambda bar is essentially the arrival rate to that queue, and then you get the variance of the input process. Now, note that I have n times the variance here, and I have a limit in n on the left-hand side. This is not really a typo. The variance is 1/n times a function that doesn't depend on n. So n times the variance of the input is actually independent from n. So this looks fishy, but it's not. N times the variance is independent from n. So you get a well-defined thing. And essentially what you want to do is kind of invert this function. You have the probability of overflow, and you want to get to the variance. So what they did in this paper from 2009, they say, okay, for starters, let's take out the infimum over all these parameters t, and we get this just less than or equal, with equality for the t that was a minimizer of the right-hand side before. So for each b, you get a t that minimizes, and this is an equality for that case. And then without the infimum, we just try to take the variance to the left, and we take the limit to the right. And now, since the right-hand side still depends on this parameter b that's not on the left-hand side, we could just take the infimum over all possible parameters b. And we get that the variance then is less than or equal to another optimization problem. With this is less than or equal, but actually the equality was possible for all t that are the minimizers for some b here. So this less than or equal could very well be equal. Still, this kind of poses an issue for us because, well, you still have a limit here on the right-hand side. This is not something that you have, right? This is the true state distribution that you don't know, and you have a limit here. So what we do is, okay, to get something realistic on the right-hand side, we will take out the limit, say, okay, n is large enough, so this should be approximately equal to whatever we get without the limit. And instead of the true state distribution here and the true probability of being above this threshold, we put some empirical. So after big N samples, we have some empirical distribution for the Q length, p hat sub n. So we use the empirical distribution instead of the true distribution. And also, instead of taking the infimum over all b, we just take a compact interval. This is just a technical issue. It's easier when you can optimize over compact sets instead of open and unbounded sets. But essentially on the right, we have something reasonable that we can compute. We have an empirical distribution, and we have an infimum. So that's the estimator for our variance that we're going to use. So we go b hat, and this is this infimum. So for every t, you just find the infimum, and that's what we hope that it's the variance, so that it converges to the variance. And what we actually show is that yes, this is in fact a good estimator for the variance. So we show that for every fixed time, if you take the limit first as the number of samples go to infinity, and then as the number of superimposed sources go to infinity, then the estimator actually does converge to the true variance almost surely for all epsilon small enough. So if you take this compact interval sufficiently large, then the infimum will fall inside this interval, and we're good to go. This converges, and it's a good estimator. So this is good. With this, we're saying, okay, we can actually invert the Q-length distribution and actually get the variance of the input process. Now, what we wanted to find was the whole covariance matrix of the arrival process. So we need to find all the m times n plus 1 over 2 different covariance functions. And in fact, for each one of the KQs, we can use these estimators to obtain a linear equation. Essentially says that our which is approximately equal to the variance of the input process. And the variance of the input process is nothing more than some linear combination of the covariances that we want to find. And these linear combinations are with the routing matrix R, which we actually know. So we need to kind of solve this linear system of equations to find all the covariances for different indices, JQ for all from 1 through m. But we won't have k equations, right? And we might have way more different functions. So we might need to repeat for different routing matrices. And these have to be picked kind of not in any way, but it has to be picked in a particular way that we have enough linearly independent equations, right? And then if we repeat this estimated state Q length for different routing matrices, we obtain more of these linear equations, and we can finally find the whole covariance matrix. So with this is a valid inversion procedure. But the thing is, we only use marginal distributions, which is, it's okay, but could we use kind of the joint Q length to get more equations directly instead of just getting one equations for each Q? And yes, the answer is yes, we can do it, but it's a little bit tricky when you get into more than one dimension. So, but these yields are completely new second inversion procedure. Then now we go from pairwise joint Q lengths to the covariances directly. So here the workflow now from the arrival process through routing, we can look at the two-dimensional input process, and through Q we get essentially the joint Q length for the ith and the jth Q. And our inversion is taking this two-dimensional random variable and through some procedure get directly the covariance of the input processes. And this again will be based on a large deviation principle, that because now we have two Qs, we look at the probability that a linear combination of Qs goes above 1. And this one is without loss of generality because we're going to consider all possible linear combination, positive linear combinations of I and j. And this is very easy to check that now it's a solution to a two-dimensional optimization problem, which now depends on the variance of the sum of the input processes. So here we'll have the sum of the variance of the sum is just the variance of the first plus the variance of the second plus the covariance. And that's what we will try to kind of get out of this formula. Now doing this yields an even more horrendous formula that wouldn't fit in one slide, even if I split it into parts. But it's similar to the one before, and essentially we can define in the same way a covariance estimator that's again a solution of some optimization problem that here will depend on the joint Q length distribution and on an empirical version of that after big N samples. And we hope that this is equal to the covariance in the same way that the first one was equal to the variance. And we prove that in certain cases, it is. So in certain cases, it is a good estimator. So we show that if the input process is actually short range dependent, so these are the fractional Brownian motions with h less than 1/2, which this includes Brownian motion. So you can think, okay, this works for Brownian motion and half of the others. And the key part also is that the input processes that we're trying to learn their covariance are non-negatively correlated. So the correlation is greater than or equal to 0. Then we were able to prove that yes, this estimator converges to the true covariance. When we take the limit first as the number of samples goes to infinity, and then with the number of superimposed sources go to infinity. This indeed works out. And again, this convergence is for all small enough, so we just need to pick this compact set big enough to include the true minimum of our function that we're minimizing. So in this case, when it works, we still needed to find the m times n+1/2 distinct covariance of the arrival processes. And for now, we just got the covariance of the input processes. So we're not done. We need to find the covariance of the arrival processes. And well, using the first inversion, we know that for each one of the KQs, we obtain one linear equation. So we get k linear equations just from using the first one. And now from using the second procedure, essentially for all possible pairs of q's, which are k times k minus 1 over 2, we get another linear equation for each pair. So we essentially get, instead of just k equations, we get order k squared equations from just one time that we estimate the state Q length for one routing matrix R. So in particular, if m is less than k, that means if the number of different classes of traffic, different types of traffic, is less than or equal to the number of q's, k, then we get enough equations to completely solve this linear system of equations for a single routing matrix. And even if this is not true, then yes, we need to pick more than one routing matrix and do another estimation step and this inversion. But still, they're going to be way less than we had before. Before we only got k equations out of each estimation step, and here we get k squared, order k squared equations. So this is way more powerful. And if we get we can get even more equations if we go to 3 or 4, but we didn't go that path. With this, we thought that it was reasonable to have less types of traffic than servers. But okay, with this, we show that again we can do it with even less estimation steps, but only in some cases. It wasn't so general as before. Before it always worked out for a first inversion, and this sometimes works. And we thought there was a surprising thing is that sometimes it can never work. So we have kind of an impossibility result for some of the other cases where when it doesn't work. So we proved that if actually our input process is long range dependent, so it means that you have a positive correlation in time. We have many arrivals today, we're going to have even more arrivals tomorrow. It's more likely to have many arrivals tomorrow. And if the input process are actually negatively correlated to two queues, so you have the rho ij less than 0, I'm sorry. Then the covariance of the input process cannot be directly recovered from the large deviation behavior of a linear combination of queues. And this is not the limitation of our inversion procedure. It's kind of an inherent loss of information that happens through the queuing and through the fact that we're actually looking at large deviation behavior of the queues and not precisely at the queues. So this first was kind of surprising. I wanted to figure out why this happens. So why do we have this limitation that sometimes we cannot get the covariance out of the joint queue lengths? And there's essentially 3 short explanations. One is the analytical one, is that the one that kind of comes out in the proof. And there's one kind of explanation that uses sample path large deviations interpretation of what we're doing. And then we have another one that's kind of more intuitive, more hand-wavy, when you think of queues as reflected processes. So the first one, kind of analytical explanation, is okay, if we look at the large deviation behaviors of these queues, they're based on this large deviation principle. That is the log of the probability of positive linear combination of queues being bigger than 1 is the infimum of this function, which has the covariance that we needed kind of hidden here in the denominator, in the variance of the sum. But what we show in the proof essentially is that if you have a minimizer of this infimum of this right-hand side, then either T or S are going to be 0. So essentially the right-hand side, instead of having the variance of the first one plus the variance of the second one plus the covariance, which is the one that we need to take out, the right-hand side turns on only two terms, the minimum of two terms that only depend on the variance and not on the covariance. So despite all the formulas, essentially what happens is that we show that the right-hand side does not depend on the covariance. So essentially, this is a constant function of the covariance. And as such, you cannot invert it because, well, it's constant. So the key, of course, is to prove this claim about the minimizers, that one of them is 0. But afterwards, it's clear that, OK, the right-hand side does not have the covariance. So there's no way you're going to be able to invert this. Now, if we think about more of the large deviation approximation as a sample path case, so thinking about what's the most likely path for a certain event, you can think about this limitations follow. So suppose that you have Qi and Qj be the most likely paths such that some linear combination of the Qs, positive linear combination of the Qs, it's equal to 1. So there's a very nice interpretation of these minimizers when you think of sample path large deviations, is that the minimizers that we had before have a very particular meaning. T star and S star are the start of the BC periods of the most likely paths that contain time 0. So T star is the last time that the Q was at 0, given that this event occurred. So given that at time 0, this linear combination is equal to 1. And the same for S star is the start of the BC period of the jth Q that contains time 0. So the last time that it was 0. And if we combine this with the fact that, well, we know that either one of the two are 0, then the most likely paths for this event are the ones that only one Q is really positive and the other one is 0. So either the ith Q is equal to 1 and the jth Q is 0, or it's the other way around. So essentially, this event, a linear combination being big, the most likely way for this to happen, and thus the only thing that you see in the large deviations is what happens when only one of them is big. So it's not surprising that you're not seeing, you're not really seeing the covariance because only one of them is big. So you're going to observe the variance of that one. The more intuitive, perhaps, explanation, and I think the ones that shows better that there's a loss of information, is when we think about Qs as reflected processes. So a well-known fact in Q theory is that you can look at Qs as the reflection of 0 of whether they're called the free workload processes, which are free workload processes like W are defined as the input process minus the rate of the server multiplied by time. So this workload process, if the system is stable, we know that, well, the service rate is bigger than the average arrival rate. So this workload process is almost surely going to go to minus infinity as t goes to infinity, because this term is going to become bigger and bigger than this one. And the Qs can be seen as a reflection of this process at 0. So essentially, what you take is this workload process and you just add another process that makes sure that this remains positive or 0, so non-negative. Now, when we look at the Qs like this, and in this case, because we have negative correlation, we know that if one of the input processes grows faster than usual, then the other one will, or at least most likely, to grow slower than usual. And when that happens, essentially, you have that the Q length of the one that's growing faster, then it's going to increase. The other one, because it's growing slower, then it's going to go down. Or if it's at 0, it's just going to get reflected at 0. So while one is going up, the other one is essentially bouncing off at 0. And what happens here is that the magnitude of the correlation is lost as this reflection at 0, because you don't know how much you had to push it upwards for it to stay at 0. You only see that it stays at 0. And maybe you have to push it a little bit because they're weakly correlated, or maybe you had to push it a lot because they're highly correlated. But this correlation kind of gets hidden in the reflection at 0 in this non-linearity of queuing. So those are kind of the intuitive explanations that we had. Now that we can kind of invert the Q lengths and get covariance matrix, we need to kind of finish the job, right? So we need to find the optimal routing matrix. And then this is kind of pretty straightforward. Once we have the estimate for all the covariances, we just use some large deviations approximations. As before, the only thing that matters here is that we can approximate the probabilities that we want, the probabilities that you go above a certain threshold for any routing matrix, as some function of our estimates and the routing matrix and everything that we know. And once we get these estimates, which we can compute for any routing matrix R, we just say, okay, we estimate that the best routing matrix is going to be the one that solves the minimax for this estimated probability. So they're kind of nested estimators one after the other, but well, we see, okay, these are reasonable routing matrix for a problem. And in fact, we show that in some sense they are. The routing matrices themselves, this estimator and the true one might not be close. We don't know, but at least we show that the cost under this estimator converges to the cost of the true best routing matrix, in some sense at least. So this is showing essentially that, well, the routing matrices, we don't know if they're close, but their costs, so the minimax is indeed close when you take the number of samples go to infinity and the number of superimposed sources going to infinity. So it is indeed, I would say a good estimate. And finally, since all these results are really only asymptotic results, we don't know anything about the convergence rates, especially for the number of samples, since we're looking at arbitrary Gaussian processes, and even for fractional Brownian motions, unless you look at Brownian motions, we really cannot say anything about convergence rate, because we're taking samples of a process, so samples are not even independent, and that already creates a huge mess. So we run some simulations in MATLAB to see how well it performs under kind of realistic numbers. So for a setup, just for disclosure, we just took n equal to 1,000, so 1,000 superimposed sources. And we looked at just a two-dimensional problem. So we have 2 queues and 2 types of traffic. And the routing, we just took it to be the identity. And then the load is 0.8, so the arrival rate is 0.8, the rates are 1. And we use this parameter to estimate the variance and the covariance. And first, what we see is here we have the true variance and the true covariance in blue, and then are estimates in dashed colors for different number of samples. So the left are the estimator for the variance, and the right are the estimator for the covariances. For the variance, we see that, well, if you have 64 samples, then it's not going to work out. You're going to get kind of garbage. But then from 256 onwards, then it works fairly well, this estimator. For the covariance, because we have kind of a more complicated function, we have kind of compounding errors. We need a little bit more samples. 256 is not really enough. Perhaps you could say that you need at least 1,000 samples in order to get kind of a more accurate estimate of the true covariance. Now we took a look of what the Qs look like in this case, and because this was actually reviewers of the paper told us, well, it's not realistic to have infinite buffers like we have. What happens if you truncate the Qs, right? So now we're going to see what happens if you say, okay, let's put a kind of a finite buffer here, and whatever comes when the buffer is full, you just throw it away, and try to do everything with these finite buffers. So we try that. We try with 16,000 samples, so that's not an issue. And we try with different buffer sizes. So I'm showing you the Qs kind of for reference, because otherwise the buffer sizes are just numbers that you don't know what they mean. And so we see that if you take, again, the estimate for the variance and for the covariance, if the buffer size is too small, if you take 1 or 2, then you're going to get something that's pretty far off. And that's reasonable, because if you look at the first Q and you think about buffer 1 and 2, then you're losing everything. It's like all these spikes, which are the large deviations, you practically lose them all. So you need kind of 3 at least, or 4, in order to get a good behavior, which we thought it was still impressive, because with 3 you still get rid of most of the spikes. And for the covariance, you'll need a little bit more. Again, it's kind of a bit more delicate, the covariance. But yeah, we're kind of quite surprised that it works so well, even with finite buffers, even if we truncate it so much. So why does it work so well? So these finite buffers are actually essentially truncating the statistic distribution. So it shouldn't work as well, but there are 2 key things here going on. One is that the large deviation approximations on which these estimates are based do not really depend on buffer size if they're large enough. So the probability of going above 1, if you have buffer that's 2 or more, then it doesn't really matter. The asymptotic, the large deviation behavior is the same in that case. So this is a well-known fact on this large deviation approximation. So it's not such a big deal. And also the fact that our estimates actually depend on an infimum over buffer sizes, right? Not on the whole distribution. So as long as this infimum is given for a part of the distribution that wasn't truncated, then we should be good to go. It shouldn't be such a big issue. So that's why it kind of doesn't matter that much. You can truncate it very harshly, and this still works pretty well, which we were very happy about. So this was kind of for the case that everything works out, right? But we showed that in some cases, it's impossible to recover directly, at least, the covariances. And for example, this is in the case of negatively correlated fractional Brownian motions. And we see that the variance, our first estimator, indeed always works. So works as expected, providing you have enough samples. But also as expected, the covariance estimator gives you garbage, and this is because it's actually impossible to directly recover the true covariance. You just get whatever. We don't know what you get, but we know that you won't get what you're supposed to. So yeah, when it works, it works very well, and when it's impossible that it works, well, indeed it doesn't. So to conclude, we showed that actually the input variances can be recovered from the Q lengths, kind of always. So the arrivals covariances can be recovered just with a few iterations. So for different routing matrices, you do different estimation steps and you get them all. In some cases, for short range dependent inputs and non-negative correlations, then the covariances of the arrivals can also be recovered from the Q length, and this on one shot. And we also showed that these things also work in practice, even with finite buffers and few samples. And we showed that, well, in certain cases, like low range dependent inputs and negative correlations, then the covariance cannot be recovered from the large deviation behavior of the Q lengths. And last but not least, actually, all of this that's essentially for a load balancing system can be extended to multipath routing in acyclic networks. You just need way more involved large deviation results, which we happen to have in another paper with Michelle. So it would take kind of more work to kind of figure out how to get the routing matrices here in this case, because it's not kind of exactly the same, but it can be easily extended to this case. So that's it. Thanks.
Thank you very much, Martin. That was an excellent presentation, really interesting. Okay, so please put your questions or comments in the Q&A for Martin. I'll start with a question, Martin, just as background, I guess, for you, because I didn't. I mean, I know that people will have a little knowledge of you from your work and also from the because you're on the program. But you're currently a postdoc at Georgia Tech. Is that right? And
yeah,
you actually hold a presidential fellowship there. Is that right?
Yeah, that's true.
Yeah. Okay. All right. And so you had a presidential. You had an award as well when you were at. You've had some. I was looking at your CV and your background. You have you've been a finalist for Informs conferences, 2 of them. Is that right? And you've also had the presidential fellowship at MIT, and you're also then at Amsterdam as well in the networks group there. So it's a pretty impressive background for you to have been in those places. And so I just wanted to say that because you know, it's very good to have you be able to present here. And I was thinking of your presentation and wondering, one of the questions is that you have these different contexts that you've, you know, where you do have really nice results. And you talked a little bit about in the middle. So, you know, the areas where you're not quite, you haven't really got those definitive results. So, and I was wondering if you can expand a little more. Have you sort of, where have you pushed the boundaries for those? So you've got, you know, where you've got very well-defined, like well-behaved results, and where you don't get results at all. And then you talked a little bit about the middle area. But can you expand a bit on that and where what you've explored in there? So,
yeah, sure. So we have, sometimes it works and sometimes it doesn't. So
so you know, when, for example, you have the short range dependency, you have positive correlation, and then you have or non-negative correlation, and you know something about when you have long-range dependency and negative correlation. And then you talked a little bit about what happens in the middle, but you know, how does it look in that middle area?
Yeah. So that's a good question. So we have kind of you can divide in 4 cases depending on if it's short or long range dependent and positive and negative correlation, and we have like 2 of these cases, and we're missing the other 2. So short range with negative correlation and long range with, with positive. And the problem is that in order to show that you actually get what you want to get, you have to study this optimization problem. So at some point you have to show that either this problem is convex, so you can solve it and you're good to go, and or it's not. And so in 2 cases, one, it's easy to show that you have a convex problem, so you're good to go, and the other one, it's definitely not convex, and you have an issue. But in the other 2, it seems that it's not clear when it's convex and when it's not. We ran a bunch of simulations, like to see if this is a good estimator, right? And sometimes it is, and sometimes it isn't. And we couldn't figure out when this was working and or it wasn't working.
Yeah, I can understand that it's challenging, and I was just curious to know what your insights are on those sorts of areas. So I was also going to ask a question about uncertainty, but I think that the sort of the uncertainty that you might have in the estimates and how that plays out in your results. I think that Shane Henderson has encapsulated a similar question here. So in his Q&A question, he says, your model of reality is not reality, so there's some model error in there. And so I think this is talking more about model error rather than parameter estimate error. But any thoughts about how model error, and I'll add about how your parameter estimation error then could influence the selection of the routing matrix and its performance?
Yeah, that's a great question by Shane. So I talked at the beginning that I use Gaussian processes as some sort of functional central limit theorem approximation of reality, right? And we know that there's for a bunch of realistic models, they converge in a proper sense. But the issue, yes, that there's a problem because it's not really a continuous mapping what we have in terms of queues. So if you take the behavior of the queues under the real models, and you take the same sort of limit that will give you Gaussian processes, results cannot be directly translated. It's not that you can have some theorem that says that this is close to reality. The paper by Michel, this paper in 2009, they actually explored what happens when you take, instead of Gaussian processes, what would be the real processes, right? Discrete packet level processes. And this inversion idea worked very well, even in those cases. So I think simulations will show or have shown that this inversion, at least the first one, does work in reality or in processes that look way more than reality. But to get some sort of proof, yeah, I don't think that I will be able to get that. So I don't know what's there. Simulations show that it works well, and there's nothing really theoretical that I can say. Mm-hmm.
So Martin says thank you. It's perfectly reasonable. Model error is hard. I guess that's true. Okay, well, I know that we're close to time, and so again, I want to thank you very much, Martin, for an excellent presentation, and for sharing your work with us. You've certainly got an outstanding number of publications, and they're very well cited, and I look forward to reading some more of your work as we go forward. So thank you very much.
Thank you.